Good afternoon, everyone. Welcome to Alice to IEEE Victoria Computational Intelligence Society speaker series, and Professor Alice Smith from Urban University, United States, to the our society for giving, and thanks for the accepting the invitation to talk about the enhancing defense through intelligence optimization. Uh, Professor Alice Smith, the Joe W. Ford and Junior Distinguished Professor in the Industrial and System Engineering Department at the Urban University, where she also holds a joint appointment in computer science and software engineering. She served as a department chair from 1999 to 2011 and previously taught at the University of Pittsburgh after industrial experience with Southwestern Bell Corporation. Dr. Smith's research focuses on the analysis, modeling, and optimization of complex systems, particularly a computation inspired by natural systems. She holds a US patent, several international patents, and has authored over 200 publications with more than 18,000 citations. She's ranked among top 2% of scientific researchers worldwide. She's the editor and the chief of the Informs Journal on Computing and has received multiple Best Paper Awards and has led over 12 million in sponsored research funded by the organizations, including NASA, the US Department of Defense, and the National Science Foundation. Uh, Dr. Smith has also participated in numerous international collaborations and Fulbright programs across Turkey, Colombia, Chile, and more. So this is the short bio. She has a long bio,
Too
excellent bio.
long.
Yeah, and please, you can go to VTool and you can read through that. But it's amazing bio. So please join me welcoming Professor Alice. Over to you.
Okay, thank you, Malika. I'm very happy to be with you and have it recorded also to hopefully share with a few more people. I have never been to Australia, but I hope one day to visit there and also New Zealand. It's a long distance and would not look forward to that trip, but I would look forward to meeting the people and seeing the amazing country that I know you have there. And I know there's a few people in the US here too, so welcome, my dear friends. Okay, so what I'm going to talk about today is four different applications. So my talk and my work are application oriented. I'm not much of a theoretician. Um, I do want to acknowledge IEEE Computational Intelligence Society for sponsoring. I mean, I'm not getting paid and it's free, but they do sponsor my role as a distinguished lecturer. And often, and I do it in person. In fact, several weeks ago, I was in Mexico to give a lecture. It was a different topic, but it was in the same program. So it's a great program. This one will actually be my last one. My term ends the end of December, and I have to wait at least a year or two before applying to be named again. But it's been a great privilege to speak and often meet people in many parts of the world that are brought together through computational intelligence. So a little bit more about my background with some photos. Um, so I am an AdCom member of the society. That role also ends the end of this year. I've served two different terms. I was elected earlier this year to the U.S. National Academy of Engineering, and I believe I'm the first person ever elected to that with actually specifying computational intelligence on my citation. I'm very proud of that. So a fun fact, I studied Spanish. I actually still study Spanish, and I graduated only a few years ago with a Bachelor's of Arts, which I never thought I would have, but it was a wonderful trip. So top left are some work I did with computational intelligence applied to, as you can see, the product is the humble toilet, and about process control improvement for ceramic casting. The bottom right is in Valparaiso, Chile, where I have great contacts and collaborations. And this was on a tour of the ports. And we've also done work with computational intelligence in ports and logistics in general. The photo on the bottom left, I couldn't resist adding. That's me, of course. You probably recognize because I don't look too much different. And the other guy there, that handsome man, is Tim Cook, who's the CEO of Apple and has been for quite some time. And he is a graduate of the same department that I'm employed in at Auburn University, and he's a wonderful person and friend and alumnus. So really proud that I've had a chance to get to know him. But even prouder is the middle photo. This is my current research group. They're a very diverse set of students from all over, none from Australia, I'm afraid, but from many other places. And we have fun studying computational intelligence and related topics together. Okay, so we'll get into it. This is an overview. I'm going to show you four applications using some different um, techniques from the inspiration of natural systems, evolutionary strategies, particle swarm optimization, simulated annealing, and genetic algorithms. I want to preface this by one of my kind of overall goals as a researcher, which is to develop algorithms that are effective, but also as simple as possible and as practical as possible. And I'm going to be showing you four very diverse applications, all related to defense, which has become, unfortunately, a bigger topic in today's world with a lot of animosity in different regions. And I know it's touched Australia as well. Airfoil design, ad hoc network connectivity, drone land vehicles for delivery in military logistics, and air mission optimization. So let me proceed. As I said earlier, with the ubiquitous computing that's so powerful and available everywhere, I think in many cases we have over-designed our algorithms and approaches because we can do so much, and we've kind of overfit them, in my view. So, yes, they work extremely well for specific problems, but they tend to be a little more brittle, a little less generalizable. And so, when I work with my colleagues and students, I always say, let's start with the simplest problem that relates to what we want to solve ultimately, knowing we can't capture everything anyways, and also the simplest design. So if you think about these, and the wheel is iconic, but I think the needle is even a, a better example. It's so simple. It's so universal. It's never, ever been improved upon in the many tens of thousands of years, and probably longer that it has existed. So if any of us could develop a needle, we would deserve all the fame we could get, but I don't expect that to happen, at least not for me. So a few quotes that I like about algorithms. I'll start at the top, going from oldest to newest. I'm not going to read the Latin. My Latin is poor. I never studied it, although it does relate to Spanish. Well, it's futile to do with more things that which can be done with fewer. Willem of Ockham, who was a monk. Albert Einstein, fast forward 600 years. Everything should be made as simple as possible, but not simpler. Those are excellent words to live by. But this is my favorite quote at the bottom by George Box, who's a statistician. Essentially, all models are wrong, but some are useful. And this is really sums up my research. I know everything I've modeled with algorithms, with intelligent approaches, with soft computing. They're all wrong in the sense they can't capture everything. They don't. It's okay, but it's okay as long as we develop useful models, and that's our goal. So let's jump into the first one. This is airfoil optimization. This was for fixed wing drone. There's an example there. This is a project I did jointly with a graduate student in aerospace engineering at my university who took my class in these methods of meta heuristics. I don't know hardly anything about um, aerospace except I do a lot of flying. And it works. It's like magic to me. But this is to design the airfoil or the wing. And so there's two ways in aerospace engineering to do this direct, which is to specify the geometry and calculate performance. Sorry, that's my son. There's a big basketball game on TV. So yeah. Um, that's what we're going to be doing here, are indirect, and you can read that. Okay, so what his idea was is to improve the Bezier curve for parameterization. So this is a very common direct method that's used where the Bezier curves, let me see if I can get you a better pointer. Yeah, laser pointer. Okay. Oh, yes. So these are the Bezier curves. You can see the X's that specify and this is the cross section of the wing, or the airfoil as it's called more technically. Um, and these are typically done, as you see here, that they can move in one direction, in this case, a Y direction, to specify the design of the airfoil. And there's some here too. So what the student has decided to do is to use control points in both directions. So X and Y directions should allow for better representations of a good airfoil. Of course, it enlarges the search space incredibly. So if you go back here, you can see underneath it and on top. Now we're going to move in two directions, which allows us to cover a rectangle in real space rather than just along a line. So we decided to do this with evolutionary strategies. Evolutionary strategies, or ES, is one of my favorite techniques. I think it's been underappreciated. It's quite simple, but for continuous search spaces, it's incredibly effective. It was developed over in Germany, in Berlin, with by Rechenberg and Schreifel. Here they are in those early days. Um, and it was done independently of genetic algorithms, which are designed by Holland over at University of Michigan in the U.S. About the same time frame, a bit later. Um, and they have similarities, but they're also quite different. So in ES, mutation is the primary search operator, whereas genetic algorithms, it's recombination or crossover. So you have mu parents producing lambda children, and that's the standard notation. I don't like it because I'm kind of a statistician too, and mu always means population mean of the normal. Anyways, it's it's good for real encoded space. The mutation takes the form of a Gaussian or a normal bell-shaped curve where it's centered about the parent. So a single parent produces multiple children. And the sigma standard deviation or the width of the Gaussian self-adapts based on the search history. And this is what is super cool about evolutionary strategy. Super simple rule called the 1/5 rule that simply looks at the proportion of quote successes of children to parents, where success is the objective function value or the fitness. So these are typical parameters for evolutionary strategies. Um, and we used a simple one. We did not add crossover or separate sigmas. We just adapted. We did use plus strategies, so you combine the parents and the children together, and the fittest survive to the next generation. So I do think, as I said earlier, this is a bit dated. It's from 2018. That evolutionary strategy has been really underappreciated compared to genetic algorithms. And I understand genetic algorithms has kind of a probably a better name, and it's applicable also to combinatorics and continuous space, and I use it too. But ES is should be one of our go-to algorithms also. So we're using a small population, so there's 8 parents that produce 40 children. So each parent produces 5 children. We're doing 12 control points. You can see the encoding here. So 6 on the upper and 6 on the lower. This is for 6 of them. And we're doing the upper here and the lower here with an XY value. So you can see our encoding here is going to be 6 times 4, 24 um, real vectors, or not real vector, real numbers. Um, yeah. And so we did use the 1/5 rule. So every 50 fitness evaluations, the sigma would reset according to the finding of the 1/5 rule. Occasionally we jogged the sigma. So if it looked like it was kind of stalling out, we'd reset it to something wider and kind of add diversification. We are doing 2 objectives, so it's a bi-objective problem. I'm going to show you that in a moment. And we used a simple rank based. So you're ranking according to the Pareto front, as you can see, and to get diversity along the Pareto front, we use again a common technique, epsilon dominance. So we kept an archive size. So this is all the non-dominated solutions. And that, of course, ranges and it changes over evolution. And this was the size. If something was infeasible, it couldn't fly, or it just wasn't something that could be constructed, we discarded it. It didn't happen that often. So to calculate the fitness, we used a standard simulation called XFoil. A disadvantage of XFoil is it's very computationally intensive. Um, so that's why we had the small population, and we really had to be mindful of not evaluating more than, excuse me, we really had to. So our 2 objectives are to minimize drag, so that pulls it down to the earth, and maximize lift, which lifts it up to fly. So we're maximizing lift and minimizing drag. This is an example of the XFoil output. It gives you all sorts of information, sorry, about how the airfoil will perform in true flight. So here's some results on a standard test problem. that was studied by another paper earlier than us by D'Angelo et al. And you can see these were our initial population here with the blue crosses. And D'Angelo's work are the black and white squares, first 5 parameters, and the stars for 7 parameters. Ours are the colored ones, the blue and red and green, and they're over the times of the evolution. So you can see the ideal point is up here at 0 and 3, which is minimizing drag, which is on the x-axis, and maximizing lift, which is on the y-axis. And you can see over evolution, we got more and more non-dominated solutions and better ones, and they're spread out quite a wide distance. So a human designer, of course, could then choose um, whatever more appealed to them of the drag versus the lift. So some critical retrospection, which is I'm doing this on all 4 of our applications. It worked really well. Xfoil was a computational hog, so that was less than ideal. But the optimization was great, and the student was interested in expanding it to the fuselage design and a more complicated polyhedral wing design. Okay, let me get a little water. I had some, but I drank it all. Hang on. Okay, thanks. So the second one's in ad hoc networks. So I worked in telecommunications. That's actually how I first got involved with IEEE before I went into university professorship. So ad hoc networks are mobile networks, but there's no fixed infrastructure. So the users themselves, as they're moving around, form their own connectivity infrastructure. And it's used a lot in military. That's why I'm doing defense here. And search and rescue, uh, terrains that don't have and won't have fixed infrastructure, disaster areas, and so on. So what the idea, and this is again done with one of my students, his idea was to add drone agents that would augment the users to form connectivity. So the problem becomes, how do we optimize in near real time the location of these drone agents so that the whole network connectivity is optimized? So we chose particle swarm optimization. It is another of my favorite. I love PSO. It's for continuous spaces. It's super quick. It's also quite simple. And the quickness was really the strongest motivator for choosing this. So just briefly, it was developed in the US by Eberhard and Kennedy. Really interesting group of gentlemen. Eberhard's a electrical engineer, engineering professor. Kennedy is has a doctorate in sociology and works kind of more in the cognitive world. So this is designed for real numbers again, and the particles move through space, and they're um, motivated by natural systems. You can see here at the top of a school of fish, at the bottom a big flock of birds, where the individual can move according to their individual wishes, but they also exchange information with the group. And so there's a social influence too. So a particle has three vectors. The x vector is where it is in space. We're going to do two-dimensional space. Could be one-dimensional, could be three-dimensional, could be 20-dimensional, whatever. The p vector is the personal best. So where was the fitness the highest for this particular particle? The v vector contains a gradient, or it's actually a direction that the particle is traveling. And then there's two fitness values, the one that has the fitness of the current location of the particle, and one that records the fitness of the p vector, which is that personal best. So the move operator is the particles fly through space, and they record their best locations. They generally communicate this with the group, with the neighborhood, or with the whole group. It depends how you set up the neighborhood. And so, how do they move? Super easy. They simply move their new space is their old space plus whatever the velocity vector is. So the key thing is to update the velocity vector. So this is the standard way to do this, where you have the old velocity vector. There's two parameters. These are constants, phi1 and phi2. So phi1 is called the cognitive. So this is based on the user's or the particle's own experience. So there's a uniform random number here between 0 and 1. This is the location of the personal best minus the location of where the particle is now. And we have phi2, and this governs the so-called social aspect. This is what the information has been exchanged from the group. Again, the random number. Here we have the personal best of the group or the neighborhood, minus the same location. So it's very simple. Phi1 and phi2 are usually static constants, and that's how we use them. So again, you just record the fitness. Velocities are generated typically randomly. So this is the problem we studied, the ad hoc network problem. And we did it in two-dimensional space. So we're assuming the drone is flying at some constant elevation or altitude. But you could do it in three-dimensional space. And we want to maximize connectivity over the mission. Using GPS, we know the location of the users and we know their past movements, but we don't know where they're going because they're autonomous. They're on their search and rescue or their military operation. So why is it a BHP? So what is a BHP? Well, I have to have a little bit of salty language here. It's a bitchin' hard problem. So it's really, really hard. And really for these um, uh, heuristics inspired by nature, they need to be hard problems because you have to craft a heuristic and they tend to be a bit more complicated than some simpler methods like a Newton search. Okay, so we need to estimate where the users are going to be in the near future, and we do that through kinematics. We have to choose the best network design, and we use both connectivity and the link quality. We use a path loss model with a surrogate because just calculating the exact calculation is very computationally expensive. And then the positioning of the drones has to be done. I mean, we time slice, but it has to be done really quickly. So it's in near real time. So this is the architecture we did. Essentially, it's everything I said. We discover where the users are based on their current and prior data. We predict their movements for a small time step, bunch of time steps ahead. We optimize the network by optimizing where the drone should be placed for that connectivity, and we deploy them. And then it starts again. So what I'm going to show you are two results. One is on the small problem and one is on the large problem. What you're going to see are the open diamonds are the users, and they'll be fanning out from the bottom left. Again, we're working in two-dimensional space. And the solid blue dots are the drones or the agents, and they're getting optimized with this particle swarm optimization in near real time. So I think I have to change this pointer to something else to start this. Let me see. Oh, there it goes. Never mind. So you can see as the users fan out, the drones fan out too. This is, we just cut it off here. So you can see here, there's a drone, two drones forming connectivity. The users can also form connectivity. And of course, that's based on distance. And then we use a path loss model, which is nonlinear, to augment that. And now we're going to see the same thing, just with a bigger problem. So again, you can see how they fan out and establish connectivity with the user. We have a little bit of autonomous design. If a drone gets out of the network and is not connected somehow, in other words, for example, the prediction was wrong and the drone goes in the wrong direction because the user made a sudden change. Um, we have some simple intelligence built in that the drone will go back to its last connected location. So it's quick and simple. We used just the plain vanilla particle swarm. It did great. It can scale up. Um, again, we predicted user movements. And the thing that we could do next is to also use some plans. So in this case, we were purely reactive, but we could also use military plans or search and rescue plans to try to improve and be more proactive. Okay, the third one. I have a fairly big program in drones and looking how drones can be used mainly in logistics. And so this is about how we can do drone supply in field operations. And of course, nowadays in military operations, drones are getting a lot of press, especially from the unfortunate and long war between Russia and Ukraine. Those drones are basically mainly bomb carrying drones or weapon carrying. Those are different than what we're trying to do. We are logistic drones, so we're trying to bring supplies and pick things up. So this is an example, which of course the military does use drones for that purpose. And what we're trying to do here is where not all the items are available for the drone to deliver at the start of the period, say day. And so the drones are going to resupply land vehicles or they can deliver direct to the field locations. So this is a little overview of the depot. So we have a single depot or central supply point, and we're going to have drone routes to meet up with the truck. The truck is the blues here and resupply it, and then also it can be um, served by a drone. So in this case, we have node 3 is going to resupply the truck here. And by resupply, it brings it newly available items, say uh, medicines or prescriptions or weapons that just became available that were just delivered to the central point. So it goes to the land vehicle and resupplies it rather than the land vehicle having to return to the depot. But the drone can also serve locations itself from the truck. So it's a quite complicated optimization problem. Our fitness or objective function chosen was to minimize overall delivery time. So for the entire day, the set of orders, and we optimize both the route of the land vehicle, the truck or whatever, and the drones. And there's a lot of constraints here. You guys can read them. A mixed integer linear program, which is how we generally model things first, could only solve really small problems because of the computational effort of the exact method. So we used simulated annealing. Simulated annealing is another kind of often overlooked um, intelligent approach inspired by nature. It's older than many of these other ones and maybe not as flexible, but it works pretty well. And so in 1953, which was a long time ago, um, the Metropolis algorithm was published, and that had to do with mimicking the process of simulating a metal. And it's not simulating a metal, annealing a metal. So if you ever took material science, I did because I'm originally a civil engineer. You anneal it by you heat it up where the molecules are very active, and then you very slowly cool it down. And the molecules, the idea is the molecules form their lowest energy state, a very compact, orderly, which means very strong, set of lattice. So that's the idea. So in 1983, exactly 30 years later, in Science, Kirkpatrick et al. Published optimization. So they were working for IBM at the time and said, oh, this thing published in 1953, it could be used just for optimization, not just as a pure simulation of a actual natural process. So very nice insight by them. So simulated annealing is basically a hill climbing or myopic or greedy algorithm that sometimes takes worsening moves. So in high energy states, you can think of the molecules all moving around. This is like the search. I can move around even if it's a move that brings me a worse space. And I'm going to slowly lower the temperature. And as the temperature gets lower and lower, my probability of taking a worsening move decreases until it almost reaches zero. And so that is used by the energy function, which was the original part of annealing, the science of annealing with the Boltzmann constant. We don't care about Boltzmann because we're just using this um, as an algorithm. It doesn't have a physical meaning. So if the energy decreases, you always move. So that's the greedy part. If the energy increases, you have a probability of movement, which is related to the natural logarithm E raised to the negative change in energy divided by KT. So K was originally the Boltzmann constant. We're just going to get rid of that. And we're going to have this so-called temperature, which for us is going to be a pseudo temperature. So we encoded it. We have a truck solution and we have a drone solution. So these are done separately. Down at the bottom, you can see the simulated annealing achieved an optimality gap of about 2% and runs in less than 2 hours for even big instances. So it's very computationally doable for even big problems. 2 hours, you could run it the night before or the beginning of the day. And getting to an average of 98% optimal is pretty darn good. So this is for 100 sites served, so that's a pretty big problem. You can see the average service time is on the y-axis, and with a truck only, it's quite long. However, as we have drones, and these are showing you from 1 to 4 drones with different amounts of payload. So this one is one drone that can only carry one thing. This up here, way down lower, is 4 drones are working, and each of them can carry 4. So that makes 16 spaces. So naturally, it's gone down. But it was quite effective in getting things to where they need to go more quickly, which is important in, of course, military and search and rescue optimizations. We also did some field testing. I have videos, but I don't have time to show them to you tonight because of I'm showing you 4 applications. But we have this is our Taro drone. So there aren't many drones available in the commercial space that are actually designed to hold things. Most drones you buy as an individual are designed to take photos or do some kind of surveillance. So we need a bigger, heavier drone. And we also built this box below, basically a locker where things are carried, a cargo bin. And it flies autonomously. We basically load a flight plan, just like autopilot in commercial airlines. And but it also has basic flight intelligence to avoid unexpected obstacles and so on. So it was a pretty practical solution. The optimization worked well. The field test showed that it's doable. Um, the drones, because of the flexibility, if the land vehicle it's too unsafe or they can't reach it, the drones can service that. So it's a really nice flexible application of delivering things or picking up things. And then sometimes the drone can't carry everything because it can't carry really heavy stuff. So the land vehicles take those. I like this picture. It has a special meaning for us at Auburn University because we have 2 mascots in the U.S. Every university has mascots, and one of them is the eagle. And in fact, it's a golden eagle, which is what this is. And you can see it conquering the drone. Okay, last application. This is using genetic algorithms for air missions. So this is a project we're actually just finished up for the Air Force of the U.S. And where we were interested is how to schedule air missions. They're called air tasking orders or ATOs for war game simulations. So war game simulations in this case are where Air Force pilots and officers are involved in these very complicated and big war games simulations so that they can be ready for the real thing. Hopefully, it won't come along, but when it does. So, the total number and type of aircraft available are specified. The decisions are where to place the aircraft at the various bases in the region, and then to schedule the missions and sorties of each base with each aircraft. We're going to have 2 objectives: to maximize the number of completed missions and to minimize the time to complete all missions, which is also known as make span, which is also what we optimized in the previous application. We're going to use a bi-objective genetic algorithm because we're going to be looking at 2 objectives again. So genetic algorithm, probably many of you are familiar with it. It's inspired by biological evolution, just like evolutionary strategies was. However, here the main operator is the recombination or the crossover. Mutation is included, but it's more of an occasional and small perturbation. And the population evolves over time. The preference for recombination is correlated with fitness. So, unlike the evolutionary strategies where every parent produced the same number of children each generation, regardless of parent fitness, here fitter parents produce more offspring, just like in the real world. So, if you have a say dominant male antelope who's fended off the 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 other male antelope. So now this male antelope has his quote harem and is the fitter and stronger of the antelope, mates more and produces more children than the weaker males in this case. Generally, there's a fixed population size. So our encoding's quite complicated because there's a lot going on, but it's basically all short vectors of real, not real numbers, of integer numbers. So we have the different air bases. This is showing just three here. Number of missions assigned that we're going to assign to each air base. So these are decision variables. We do some kind of sorting value, which is a priority based on the problem data. And then we have the scheduling itself at each air base. We have to allocate the aircraft. So at each air base, there's a certain number of, we're just calling them XYZ. So there's various aircraft. There are also tankers. So these tankers are refuelers. So you may have seen videos or heard about where it can refuel during in flight in the air. And this is what we're talking about. So the aircraft all have stated ranges. We used a uniform crossover and we used a random swap, a two-way swap to mutate the children. We repaired any infeasible solution by either adding or subtracting a mission, depending on how it was infeasible, or assorting value one by one. So we did repair. We didn't have to do it that often, but that's what we did instead of throwing out the infeasibles. This is the structure. We developed a heuristic for a single solution. It's a constructive heuristic based on rules. So we're building a solution. It's very quick. We do a single solution, a random search meta heuristic. So this is not a GA. And it combines both averages. It runs multiple times with different weights to get an initial set of solutions. So all of this seeds are by objective genetic algorithm. We use tournament selection based on only one objective at a time, and that's set randomly. And then we have elitism. So out to the side, we keep a repository of non-dominated solutions or Pareto optimal. So here's some sample results. Here we have make span, which we want to minimize, and percent completion, which we want to maximize. So where my laser pointer is the lower right, and that's the ideal corner. And you can see here that we've formed a very nice Pareto set, well distributed. And what we build software because this is being used in wargaming or will be. So when the user hovers over a particular solution, there's one that I'm hovering over and it's circled in black. It pulls up this, and this is the solution. So we have sorties, we have locations, we have the missions, we have the type of air mission, which is either refueling or regular. In this case, they're all regular. The type of aircraft, the period that we're working in, and then the hour of the period. A period is basically a day, is what we took it to be. So this project is just ending. We did add some risk assessment. I haven't shown that here because it's fresh off the presses. And also assigning personnel. We did in the similar way to assigning aircraft. So we needed to assign the flight personnel and the non-flight. So there's a lot of non-flight personnel that need to do the maintenance, the fueling, etc., prior to a sortie for this to all to work. The genetic algorithm works well, and how we handled the by objective. super simple but effective for our problem, simply randomly alternating. That doesn't mean every other one, it means with a random number, altering the two objectives. Um, and overall, the sponsor has been pleased for this idea to help their officers make better decisions quicker. So here's some references, the ad hoc networks, the airfoil design. Um, this one, the drone and land, we have the paper under review, and we have not written about the air tasking order optimization. That one's sponsored, as you can see, by Frontier and the Department of the Air Force. So I have to make a plug for this book because it's awesome. I don't have a financial interest in it, but I edited it and developed it and devised it and everything. It's published by Springer. It comes in both hardbound and an ebook, and it's about women in computational intelligence. And it's a bunch of different research, 19 research in computational intelligence that are all very diverse and interesting. And they are all done by women-led investigative teams, along with describing the research. We have biographies and career advice from the authors, which is really unusual, but we did it not just to record and publicize this great research, but also to serve as inspiration, role models, and encouragement for everyone to consider studying computational intelligence, but especially our women and girls. My last one, this is me. This is my email address. This is my website. I'm very responsive. And this is one of my favorite quotes. And as an educator, it kind of sums up what I think, why I'm an educator. If we wonder often, the gift of knowledge will come. This is a proverb from the native people of North America, the indigenous native people. And I really think as researchers, computational intelligence is such a wonderful field because it's all about wonder. It's all about creativity. It's about investigations. It's about, I don't know if it's going to work, or, whoa, that natural system is really cool. Maybe it could be translated effectively to an algorithm that could do some good. So a lot of times these things fail, they don't work, but you know what? Sometimes they do, and that makes it all worthwhile. So thank you very much for listening to me tonight. Um, I've really enjoyed it. Um, and I think I'm there. I can stop the share. And if you have questions and you don't ask them today, which is fine, I know it's sometimes it's difficult in a venue like this. You're welcome to email me. Also, if there's a need, Malka can contact me and I can provide a um, a copy of my slides. And I know it's on video somewhere, and hopefully you'll send me a link, Malka. I have a
Yeah,
YouTube channel that I just developed, so I'm starting to populate it, and I will add it to my YouTube channel. I think I've got like 3 followers. Maybe you guys can all become followers too.
yeah. Thank you, Alice. Thank you for the informative
It's been a
presentation.
pleasure.
Yeah, so the audience, now it's a question and answer time. So you please ask questions directly from Alice.
So it
Dr.
looks
Smith.
like, yeah, please call me Alice. Hi, Daniel. Are you in
Hi, Alice.
Australia?
No, I'm not. I'm in the States, in New York State, actually. I was
Oh,
very impressed by
wow.
your, yes, very impressed by your presentation. Question
Thank
for
you.
you on one of the first ones, there was the simulated annealing. And
Yes.
I noticed in the graphic that it showed the search abandoning one hill and jumping to another. And
Ah, yeah.
what's the algorithm for that? How do you know that you're jumping in a good direction and you're not jumping into a valley of a lower hit?
Well, you may be. You definitely may be.
Hmm.
So simulated annealing, when the temperature is high, you're moving basically randomly. So you might hit the jackpot and move to the best place. You might not hit the jackpot and move to the worst place, or more likely somewhere in between. So as the temperature gradually cools, then the algorithm becomes much more selective and much prefers to move only to good places. But essentially, it's jumping around a lot and then settling into what's in the physical analogy of a low energy state, which ours is either a maximization or minimization. Um, there are techniques, we did not need to use this, but there are techniques where you can do reheating. So let's say you feel like the algorithm has settled too quickly into a local optimum and then can't escape because the temperature's too low. You can actually raise the temperature, which makes it more random so that it can cover more of the decision space. But
Excellent.
yeah, there's basically it's saying randomness is good, but but it needs to be controlled. And essentially, all of these methods that I've shown you tonight, the four methods, they all do that. There's randomness in all of them, but there's also direction. So it's kind of trying to achieve that sweet spot between the two of them to make an effective algorithm.
Great. Your YouTube channel, is it accept, can it be found by your name, or how would I ever find your YouTube channel for a further presentation?
That is a good question. I should add that on my slide. Yes, it should be able to be found, yes, by my name. I
Excellent.
think on my
Okay.
website it's also there too.
Okay.
It's pretty new. Actually, I had something just this fall, I mean in October that I wanted to post, and I'm just not real into social media, honestly.
Sure.
Um, but it was like, how can I post it? So I asked my students, I go, you have to put it on YouTube. And I'm like, oh, okay.
Right.
And that was like, you can make your own YouTube channel and it's free. Sure. So yeah.
Great.
So
I
I
have
do
to,
plan to add a link of this. Yes.
I just thank you very much. I do have to leave for another presentation, but excellent work.
Thank you, Daniel.
Any other question from the audience? If not, I have a question. So, when you are designing like airfoils or supply network, in your optimization framework, you must handle some real world constraints. So, do you think that similar kind of constraint handling strategies can be applied for energy optimization in large language models? For example, like a
Mm.
balancing inference speed or accuracy, energy consumption, that sort of thing.
That is a great question, Malika. I don't know much about large language models. I've only done one set of research with social media and large language models. And honestly, I was working with two people, including one in computer science who was the leader of that part. I was more on the optimization data side. Um, I do believe that, yes, that there's possibilities of basically optimizing anything, including the large language models, and that could be a really fruitful area, really, to work in. And I would imagine there's probably already work being done. But yeah, it could be fun. So maybe we should work on that together. Yeah, because you do the large language models, but yeah,
Some
it would be complicated because it's not as well behaved, but it could it could work. I
mm,
mean, at least to some degree, better than not optimizing.
yep, sure.
Well, thank you all. And again, feel free to reach out to me individually. And I enjoyed spending some of your lunchtime with you. Ah, there it is. Women. Yes. Yes, there are quite a few women um, doing computational intelligence work. In fact, I have a whole presentation on it um, that I think I gave Malka to some group there a few years ago. Um, and it talks about some of the research, but it has videos on the authors and how they got into computational intelligence and why they found it such an interesting field. And it's really inspirational to see women in, seriously all over the world, um, and how they've forged a career in a field that's still male dominated. And many of them are working with a lot of women. If you saw the picture of my current set of doctoral students, I have a lot of women. I have men too. I'm an equal opportunity employer, but um, women are really well suited. But we still, need to network and we need to have role models. And as a more senior researcher, that's something that I have chosen to devote a lot of my passion and efforts toward. So thank you, Joan, for a great question.
Thank you.
Okay,
Thank
I will
you.
say,
So,
yeah, good night to you guys and let you
yeah,
get on with your afternoon.
yeah, we are happy to have you, Alice. And on behalf of IEEE Computational Intelligence Society, Victorian Section, Australia, we want to thank you for your excellent presentation today. It was very informative session. Thank you.
Okay. Adios. Bye bye, guys.
Bye.